Hello everyone, welcome to the section of Urysohn characterization of normality. In this section, we are actually going to prove the Urysohn lemma or Urysohn theorem for normality. We call this theorem as Urysohn lemma because it is proved for actually proving the Urysohn metrization theorem, which is not included in our syllabus. So which is an important theorem, Urysohn lemma. We will see what's the statement. So this theorem says that a topological space X is normal if and only if, that means it is a criteria, if and only if it has the property that every two mutually disjoint closed subsets A and B of X, there exists a continuous function f from X to closed interval 0, 1 such that f maps every element of A into 0 and for every element of B into 1. So that means this theorem says that a space is normal, X is normal if and only if there exists a function f, where this function f is a mapping from X to real line. Actually the range is closed interval 0, 1, and if you consider any two disjoint closed sets A and B of capital X, this function maps every element of A into 0 and for every element of B into 1. So when such a function exists, the space will be normal. When the space is normal, such a function will exist. Okay. So how will you prove this? So first we prove the converse part. That means assume this condition. Suppose there is a continuous function with the required property. Then we will prove that the space is normal. Okay. So assume the condition. Assume the condition. We will prove X is normal. Our claim, X is normal. So what is the statement of normality? You know, the normal spaces are spaces in which if you consider any two disjoint closed sets C and D, there will exist disjoint open sets, mutually disjoint open sets U and V such that C contained in U and D contained in V, which is the basic definition of normality. We need to prove that if you consider any two disjoint closed sets C and D, there will exist kind of open sets. Okay. So for I consider the real line, the closed interval 0, 1. Okay. You consider the closed interval 0, 1. Then you divide this interval into two pieces. You can select any number between 0 and 1. I choose 1 by 2. Then we divide this interval into open closed 0 open 1 by 2 and open 1 by 2 closed 1. Okay. So you consider closed 0 open 1 by 2. This can be written closed interval 0 1 intersection some interval open interval minus 1 comma 1 by 2. Okay. So when you consider this set can be represented by closed interval 0 1 intersection open 1 minus 1 1 by 2, which is clearly an open set in real line with the usual topology, right? Which is an open set in real line with the usual topology, open in R, and an open set intersection with the closed interval 0 1 will be an open set in the subspace topology of closed interval 0 1. ശരിയല്ലേ? So subspace topology definition അനുസരിച്ചിട്ട് ഒരു set E is open if and only if E can be written some Y intersection G where Y is the subspace, where G is the any open subset of the whole space capitalized. Here open interval minus 1 1 by 2 is an open set in real line with the usual topology. Then if you consider closed interval 0 1 as the capital Y, then this set is open set in subspace closed interval 0 1. Similarly, if you consider the interval open 1 by 2 comma closed 1, which is also open set in the closed interval 0 1, because this can be written closed interval 0 1 intersection some 1 by 2 comma some 2 intersection closed interval 0 1 intersection 1 by 2 2. Okay. So clearly this intersection will be open 1 by 2 closed 1, right? So which implies closed 0 open 1 by 2 and open 1 by 2 closed 1 are open sets in closed interval 0 1 with the subspace topology of real line, with the subspace topology of subspace topology of real line. So we have two open subsets of closed interval 0 1. And we have assumed that the condition for every two disjoint closed sets A and B of capital X, the function f from x to 0 1 maps every element of A to 0 and for every element of B to 1. Okay. So using these open sets, I will define two sets U and V to contain the closed sets, disjoint closed sets C and D to make our space capital X normal. Okay. Now to prove capital X is normal, let A, B, A and B be two disjoint closed sets in capital X. Okay. Therefore, by assumption, there exists a continuous function f from x to closed interval 0 1 such that f of x equal to 0 for every x in A and f of x equal to 1 for every x in B. Okay. Now we already chose two open sets of closed interval 0 1 which has closed 0 open 1 by 2 and open 1 by 2 and closed 1. Okay. So using these two open sets of closed interval 0 1, I define u equal to f inverse of closed 0 open 1 by 2 and v equal to f inverse of open 1 by 2 closed 1. Okay. Since f is a continuous function and these two sets are open with respect to subspace topology of closed interval 0 1, by the property of continuity, inverse image of open sets will be open. Since f is continuous and which is an open set, inverse image of these two sets will be open. Since f is continuous and closed 0 open 1 by 2 and open 1 by 2 closed 1 are open in 0 1, implies u and v are open in capital X because they are inverse images which is a subset of capital X. So we get u and v are open. What about u intersection v? If there is an element x belongs to u intersection v, which means x belongs to u and x belongs to v. X belongs to u means x belongs to f inverse of the interval 0, open 1 by 2 and x belongs to v means x belongs to f inverse of 1 by 2, closed 1. So which means f of x belongs to this interval closed 0, 1 by 2 and f of x belongs to the interval open 1 by 2 closed 1. Right? So f of x is an element belongs to this one and this one. So which implies f of x must be belongs to the interval closed 0 open 1 by 2 intersection open 1 by 2 closed 1 because it is an element belongs to both these two sets. So what about this intersection? Closed 0 open 1 by 2 and open 1 by 2 closed 1. You know these two sets are clearly disjoint sets. Therefore, there will not exist any element belongs to their intersection. But this intersection is empty. Right? But what is this? This is actually empty. Therefore, no element belongs to this set, which is a contradiction. Therefore, no x belongs to u intersection v, which means u intersection v equal to empty, which means u and v are mutually disjoint open sets. Mutually disjoint open sets. Now we will prove A is contained in U and B is contained in B. Okay, next we claim that A is contained in U and B is contained in V. When you prove this, our space will become normal. So I take an element let x belongs to A. Then what will happen? When x belongs to A, by definition, f maps every element of A into 0. So f of x will become 0. When f of x equal to 0, f of x can be belongs to the interval closed 0, open 1 by 2 because its value is 0. Therefore, it must be belongs to this interval, which means x belongs to inverse image of that set. Right? So, x belongs to what is this set? This is taken as U. So, which implies A is contained in U. Okay. And what about B is contained in V? We take let y belongs to B, then we have f of y will become 1 because f maps every element of B into 1. Therefore, fy will become 1. So, which means fy belongs to the interval open 1 by 2 comma closed 1, because it is a value is 1. The value of f of y equal to 1 means it must be belongs to this interval, which means y belongs to f inverse of open 1 by 2 closed to 1, and which is taken as v, which implies y belongs to v, which means b is contained in v. So when you have to disjoint closed sets A and B, by using this continuous function, by using this assumption, we can make two disjoint open sets U and V such that A contained in U, B contained in V, which means our space X is normal, because we verified the definition. Okay. Now conversely assume our space X is normal. Conversely assume X is normal. We have to prove that if you consider any two disjoint closed sets A and B, there exists a continuous function f from x to 0, 1 such that f maps every element of A into 0, and for every element of B into 1. Okay. So let A and B be two disjoint closed sets in capital X. Okay. Now we want to prove that, we have to prove that there exists a continuous function f from x to 0, 1 such that fx equal to 0 and 1 for every x in A, for every x in B. This is we want to prove. Okay. To prove this function, to prove the existence of this function, we are going to use the lemma 2, which is also proved in the second part of Urysohn characterization of normality. We have the lemma 2. Statement of lemma 2 says that let X be a topological space, then suppose we have a collection of subsets of capital X such that which satisfies these four properties, then by using this property we can define a function f, which is defined by infimum of set of all t in Q such that x belongs to ft. This function will be a continuous function and which takes values on closed interval 0, 1. We are going to use this lemma 2 for getting a continuous function f from x to closed interval 0, 1. Okay. For that we want to make a collection which is a subsets of elements are subsets of capital X, and this collection has these four properties. When we have such a function, such a collection, then by using lemma 2 we will define function f. Okay. So we want to make a continuous function with record property. For that we are going to make a collection, and that collection is nothing but subsets of capital X with the four properties. Okay. So to prove existence of the continuous function f from x to closed interval 0, 1, we construct a family collection of all ft such that t in Q of open subsets of capital X with all the properties of lemma 2. Properties of lemma 2. Okay. So we are going to make some collection which is a countable collection of subsets of capital X. Okay. So how will you define this? How will you construct this collection? So I define when t belongs to Q, comma t less than 0, we define ft equal to mt. In order to satisfy all these properties of lemma 2, we are making for t less than 0 ft equal to mt. Okay. And when t belongs to Q and t is greater than 1, we define ft equal to capital X. Then this collection will satisfy the second and third properties of lemma 2. Okay. Now for t less than 1 we define, for t greater than 1 define. Now we want to define ft for every t belongs to closed interval 0, 1 അല്ലേ. t ലെസ് ദാൻ 0 പറഞ്ഞാൽ ഇവിടെയുള്ള എല്ലാ ടീകൾക്കും റാഷണൽ ആയിട്ടുള്ള എല്ലാ ടീകൾക്കും എഫ് ടികൾ എം ടി സെറ്റ് ആയിട്ട് ഡിഫൈൻ ചെയ്തു. കറസ്പോണ്ടിങ് ടു എവറി റാഷണൽ നമ്പർ വിച്ച് ഈസ് ലെസ് ദാൻ 0 വി ഡിഫൈൻഡ് എഫ് ടി ഈക്വൽ ടു എം ടി. and corresponding to every rational number which are greater than 1, we define ft equal to the whole space capital X. Now in between closed interval 0, 1 corresponding to every rational number, we have to define ft with the required property. So clearly empty set and whole set will be open, right? So which are open subsets of capital X. Now we have to define for every rational number in between closed interval 0, 1 ft with all these properties. Okay. So now write the rational numbers. Now write the rational numbers in closed interval 0, 1 as a sequence of q0, q1, q2, etc. You know, rational numbers are countable, so elements in countable set can be considered as a sequence of distinct members. So in the set of all rationals in closed interval 0, 1 is also countable. Therefore the elements from closed interval 0, 1 can be considered as a sequence of distinct elements, where q0 is a rational number 0 and q1 is equal to 1 and q2, q3, etc. are the in between rational numbers from closed interval 0, 1. Okay, open interval 0, 1. Now we define fq1. Now define fq1. What is fq1? Corresponding to the rational number 1 in closed interval 0, 1, we have to define fq1, the subset, right? We define fq1 equal to, what is fq1? f1, because q1 equal to 1, we write fq1 equal to f1. What is f1? I choose f1 as the set x minus b. What is b? B is a closed subset in capital X. We have chosen that a and b are two disjoint closed subsets in capital X. So since b is a closed set, x minus b will be open. Therefore f1 will be an open subset of capital X. Since b is closed, comma, f1 is open in capital X. Okay. And note that a intersection b equal to empty. Because a and b are disjoint, a intersection b will be empty. So when a intersection b equal to empty, a will be contained in x minus b, and x minus b is chosen as f1. So which implies a is contained in f1. A is contained in f1. So what is f1? f1 is an open subset. Okay, what is A? A is a closed subset. So which implies f1 is a open set containing the closed set capital A in a normal space. We assumed that capital X is normal. In a normal space capital X. So you know, there is a proposition we already discussed in the section of normality. When a space X is normal and if you have a closed set A and an open set G containing A, then there will exist a open set and a closed set such that this A will be contained in that open set and that open set will be contained in some closed set and that closed set will be contained in this G. So there is a property that when you have a closed set C and an open set G, then there exists an open set by proposition. There is some proposition. There exists an open set H such that C will be contained in H and H closure is contained in G. We have this proposition by equivalent conditions of normality. So we are going to use this proposition here. We have X is a normal space and F1 instead of G, we have F1 is an open set containing the closed set A instead of C. So therefore by using equivalent conditions of normality, comma, there exists an open set. I call it as F0, F0, okay. For the point Q0, we have Q0 is taken as 0. So corresponding to 0, I define this F0. Then there exists an open set, we call it as F0, such that our closed set A will be contained in that open set H, that H is F0 here, and comma, its closure will be contained in the open set. Here the open set is F1. So we get A is contained in F0 and F0 closure is contained in F1. Okay, now choose this FQ0 equal to F0. Then we defined Ft for T equal to Q0 and T equal to Q1. We have to define this Ft for rational elements in closed interval 0, 1. So we choose corresponding to 0, we choose F0 equal to this open set given by normality, and F1 is chosen as x minus b. So x minus b is open and F0 is open. So our Ft is defined for Q0 and Q1. Okay. So which implies Fq0 and Fq1 satisfies all the properties of lemma. Right? Because Fq1 and Q1 are open subsets of X, and Q0 is equal to 0, 0 is less than 1, and 1 equal to Q1. So when Q0 less than Q1, we have the fourth property of lemma, that when S less than T, then Fs closure must be contained in Ft, right? By the fourth property of lemma. Here Q0 equal to 0 and Q1 equal to 1 and 0 is less than 1. Therefore Q0 is less than Q1. Therefore by that property we want Fq0 closure must be contained in Fq1. We have this because Fq0 is F0. F0 closure is contained in F1 is true by the normality. We have this. So by 1 it is also true by 1. So that Fq0 and Fq1 also satisfies all the properties of lemma 2. Now we want to define Ft for each T in rational numbers of open interval 0, 1, because we already defined for 0 and 1. Okay. Now assume that Ft is defined for T equal to Q0, Q1, Q2, etc. Qn minus 1, satisfying the conditions of lemma 2. To define successively, you can define using normality Fq1, Fq2, Fq3, etc. up to Fq minus 1. At the nth stage, to define Fqn, right? How can I define Fqn is, let Qi be the largest among Q0, Q1, etc. Qn minus 1, which are less than Qn. I choose some Qi and Qj from the list of Q1, Q2, etc. Qn. Qi is chosen as largest among these values which are less than Qn, and Qj be the smallest among Q0, Q1, etc. Qn minus 1, such which are greater than Qn. So we are choosing two elements from these Qi's such that, so we get Qi is less than Qn is less than Qj. Qi is the smallest among Qi is the largest among these values which are less than Qn. Qn നെക്കാളും ചെറുതായിട്ടുള്ള ഏതൊക്കെ വാല്യൂസ് ഉണ്ടെന്ന് നോക്കുന്നു, അതിൽ ഏറ്റവും ലാർജസ്റ്റ് ആണ് Qi. ഓക്കെ, ആൻഡ് Qj എന്ന് പറയുന്നത് ഇതിനകത്ത് Qn-നേക്കാളും ഗ്രേറ്റർ ആയിട്ടുള്ള എത്ര Qiകൾ ഉണ്ടോ നോക്കുക, അതിൽ ഏറ്റവും സ്മോളസ്റ്റ് ആണ് Qj. Okay, and then Fqi and Fqj are already defined. They are open subsets of capital X. Are open subsets of capital X and it must follows all the properties of lemma. Therefore fqi closure must be contained in fqj because qi is less than qj. മനസ്സിലാവുണ്ടോ? ഓൾറെഡി നമ്മൾ റാഷണൽ നമ്പേഴ്സ് ആണല്ലോ അതിനകത്ത് മുഴുവൻ ഉള്ളത്. അപ്പോൾ സക്സസീവ്ലി ആയിട്ട് നമുക്കത് ഡിഫൈൻ ചെയ്ത് പോകാം യൂസിങ് നോർമാലിറ്റി. ഇനി അങ്ങനെ n-1th സ്റ്റേജ് വരെ ഡിഫൈൻ ചെയ്ത് കഴിഞ്ഞാൽ നമുക്ക് nth സ്റ്റേജിൽ ഇത് ഡിഫൈൻ ചെയ്യണം. nth സ്റ്റേജിൽ ഡിഫൈൻ ചെയ്യാൻ വേണ്ടിയിട്ട് നമ്മൾ അപ് ടു n-1th സ്റ്റേജ് വരെ ഡിഫൈൻ ചെയ്തത് നോക്കി പുറകിലേക്ക് നോക്കിയിട്ടാണ് ചെയ്യുന്നത്, സക്സസീവായിട്ടാണ് ചെയ്യുന്നത്. സോ ആ തൊട്ട് മുമ്പിലത്തെ സ്റ്റേജ് വരെ ഉള്ളതിൽ qn-നേക്കാളും ചെറുതായിട്ടുള്ള എത്ര പേരുണ്ട് നോക്കി അവരിൽ ഏറ്റവും വലുതും qn-നേക്കാളും വലുതായിട്ടുള്ള എത്ര പേരുണ്ട് നോക്കി അതിൽ ഏറ്റവും ചെറുതും ചൂസ് ചെയ്യുന്നു. ദെൻ നമ്മൾ എല്ലാ qn-1നും fqis ഡിഫൈൻഡ് ആണല്ലോ, അത് എല്ലാ പ്രോപ്പർട്ടീസും ലെമ്മയുടെ എല്ലാ പ്രോപ്പർട്ടീസും സാറ്റിസ്ഫൈ ചെയ്യുന്നുമുണ്ട്. അങ്ങനെയാണെങ്കിൽ fqiസും fqjസും ഈ പ്രോപ്പർട്ടി ഓൾറെഡി സാറ്റിസ്ഫൈഡ് ആയിരിക്കും. fqnനാണ് നമുക്ക് പ്രൂവ് ചെയ്യേണ്ടത്. Okay, so we get fqi closure is contained in fqj. So closure of a set is always closed. So fqi closure is a closed set and fqj is also open subset. Right? So fqj is an open subset containing the closed set fqi in a normal space. In a normal space. Normal space capital X. So therefore again by equivalent condition of normality, in between a closed set and an open set there will exist an open set H such that this will be contained in H and H closure is contained in this. So that H is, we call it as fqn. Okay, condition of normality comma there exists an open set, we define it as fqn such that our closed set is contained in this open set and closure of this open set will be contained in its open set. ഓക്കെ, ഇവർക്ക് രണ്ടുപേർക്ക് ഇടയിൽ ഒരു ഓപ്പൺ സെറ്റ് ഉണ്ട്, അതാണ് എച്ച്. ആ എച്ചിനെയാണ് ഞാൻ fqn എന്ന് വിളിക്കുന്നത്. ഓക്കെ, യൂസിങ് നോർമാലിറ്റി വി ഗെറ്റ് fqn ആൻഡ് fqn ക്ലോഷർ ഇസ് കണ്ടെയ്ൻഡ് ഇൻ fqj. സോ വി ഹാവ് qn is less than qj and we get fq as an open set. fq is an open set and when qn less than qj we have by the normality fqn closure is contained in fqj. So if you define fqi's using the normality, all these fqn's will satisfy all the properties of lemma too. So therefore collection ft such that t in q satisfies all the properties of lemma too. All the properties of lemma too. Then by this lemma comma there exists a continuous function, f from x to closed interval 0 1 such that f of x is defined as infimum of, by that lemma we defined f is equal to infimum set of all t in q what x belongs to ft. This was our definition of fx. So we get a continuous function. In order to prove our Urysohn lemma, we need only prove that any two closed sets a and b there exists a continuous function f from x to 0 1 which takes values of which takes value 0 for every x in a and 1 for every x in b. Now we need only prove that f maps every element of a to 0 and f maps every element of b to 1. Okay, using this definition of function fx. So now we claim that, or now we'll prove that f of x is equal to 0 for every x in a and 1 for every x in b. Okay, so I take let x belongs to capital A. Okay, and we have when x belongs to capital A and we have by the construction of these fq's we have a is contained in f1 here, right? So and we have a is contained in f1, therefore x belongs to f1. Also a is also contained in f0, right? f0, therefore x must be belongs to a is contained in f0, therefore x must be belongs to f0. When x belongs to f0, what is f0? f0 is a representation and it is nothing but fq0, right? So x belongs to fq0. And you know, when x belongs to f q naught and q naught is a rational number, then that q naught will be belongs to the collection. If you consider, okay, here take what is our fx? F of x is equal to infimum of set of all t in q such that x belongs to ft, right? I choose this set as gx. Therefore, f of x can be taken as infimum of, take gx is equal to this set, okay? Then fx can be written as infimum of gx. Okay. Then what are the elements in gx? When you consider t is a rational number such that x belongs to ft, that t will be belongs to this collection. Okay, here what is 0 is a rational number. Q naught is a rational number because Q naught is a 0. Q naught is a rational number such that x belongs to fq. Okay, then this Q naught will be belongs to this gx, right? Clear? Here Q naught is equal to 0 is a rational number, and x is a point in fq naught. So which means that q naught equal to 0 belongs to gx. So which implies when q naught equal to 0 is an arbitrary element in gx, then that 0 will be always less than or equal to our infimum of that set. 0 is a particular number, particular element in this collection. And what is infimum of gx? Infimum of gx is the greatest lower bound. So 0 will be less than or equal to infimum of gx. And infimum of gx is equal to f of x. Right? F of x. And this f of x will be greater than or equal to 0 by using this idea. So which means f of x must be equal to 0. So when x belongs to capital A, then f of x will be equal to 0. Therefore f maps every element of capital A into 0. Now let x is an element in capital B. And we have f1 is a set defined to be x minus b. Okay. So when x in B, then x cannot be belongs to x minus b. So which implies x cannot be belongs to f1. Okay. Then for every t in Q such that t less than 1, ft closure will be contained in f1 because all these ft satisfies the properties of lemma 2. And by the fourth property of lemma says that, lemma 2 says that when t less than yes, then ft closure must be contained in fs. When t less than yes, then ft closure must be contained in fs. Okay, so here you know x naught belongs to f1, right? When t is less than 1, then ft closure must be contained in f1 by the fourth property. Okay, and x is not in f1 means x cannot be belongs to this closure also. So which implies x cannot be belongs to ft closure for every t in Q such that t less than 1. Okay, for every t in Q such that t less than 1 ആണെങ്കിൽ x ഒരു ft closureലും ഉണ്ടാവുന്നില്ല. So when x not belongs to ft closure means x not belongs to ft because ft is contained in ft closure. Every set is contained in its closure. So when not belongs to ft closure means this x cannot belongs to ft for every t in Q such that t less than 1. And this is only for t less than 1, okay, rational t less than 1. So when x not belongs to ft for every t in Q such that t less than means this t, rational t such that t less than 1 cannot be belongs to our gx. ഏതെല്ലാം റാഷണൽസ് ആണോ എക്സ് എഫ് ടികൾ ഉണ്ടാവുന്നത് ആ ടികളിനെയാണ് നമ്മൾ ഈ സെറ്റിനകത്തേക്ക് എടുക്കുന്നത്, ജി എക്സ് എന്ന് പറയുന്ന സെറ്റിലേക്ക് എടുത്തിരിക്കുന്നത്. ഹിയർ ടി ഈസ് എ റാഷണൽ നമ്പർ. വെൻ ടി ഈസ് ലെസ് ദാൻ 1, നോ എക്സ് ബിലോങ്സ് ടു എഫ് ടി, right? So which implies corresponding t for every t in Q such that t less than 1 comma t cannot be belongs to, implies t cannot be belongs to our gx. So which means for every t in gx we can have t will be greater than or equal to 1. എന്തുകൊണ്ടാ? When t is less than 1, that t cannot be belongs to gx. അപ്പോൾ t 1നേക്കാളും ലെസ് ആയിട്ടുള്ള ഒരു ടീകളും gxൽ വരുന്നില്ല എങ്കിൽ gxലുള്ള എല്ലാ ടീകൾക്കും എന്ത് പ്രത്യേകത ഉണ്ടാവും? That will be greater than or equal to 1. When t is less than 1, t does not belongs to gx means for every t in x, I can write the contrapositive statement. t less than 1 ആണെങ്കിൽ t gx ൽ ഇല്ല. അപ്പോൾ contrapositive എങ്ങനെ എഴുതുക? ഏതൊക്കെ tകൾ gx ൽ ഉണ്ടോ t ഇതിന്റെ ഓപ്പോസിറ്റ് ആയിരിക്കും. t will be greater than or equal to 1. So what you get now? 1 and we have our function f is a function from x to closed interval 0 1, right? So 1 is the largest value f can take. So which implies 1 will be always less than or equal to fx by the definition of fx. And what is fx? Infimum of gx. Okay. And you know every t in gx, t will be greater than or equal to 1. Therefore infimum of gx will be greater than or equal to 1. So which implies fx is greater than 1, fx is less than 1. So which implies fx must be equal to 1. So when x belongs to b, f of x will be equal to 1. When x belongs to a, then f of x will be equal to 0. Okay. So we get f takes the values 0 and 1 only for every x in a and for every x in b. So when c and for every t in gx, t will be greater than or equal to 1. Therefore by definition f takes value maximum as 1, therefore 1 will be less than or equal to fx, and this is by definition infimum of gx, and every gx has values greater than or equal to 1, therefore gx is infimum is also greater than or equal to 1, so we get fx equal to 1. Therefore f takes values for every x in a 0, for every x in b 1, which means for every disjoint closed sets a and b, comma, there exists a continuous function f from x to 0 1 such that f of x takes the values 0 and 1 only for every x in a, for every x in b, which implies the converse part of the Urysohn lemma proved, hence proved. So which is a very important essay question in topological spaces. So if you want to prove this Urysohn lemma, we have to state the lemma 2. Okay.